Okay, so in AstroGeoFit, we can select the number of knots in the time depth conversion, which tunes the complexity of the model. The more knots, the more granularity of the model you have. But if you have too much granularity, it's like the model is going to try to fit noise, basically. And this is what you don't want that. So you want something that allows you to select the complexity of the model. And so starting from trying to select the number of knots, knowing the data that is most probable, you arrive to trying to select the highest evidence or the lowest peak, which both have a penalty for models which are too complex. This is the number of parameters in the model, which goes up as the model complexity increases. But as the model complexity increases, you also improve the likelihood, so this becomes lower and lower. So, okay, the point I wanted to make is that this Occam's razor principle does not come from somewhere like, oh, this is some sort of philosophical principle that simplicity is somehow better in general. No, it's a consequence of trying to say correct stuff. It's like you want to compute the posterior distribution of something because this is the right quantity, and it just so happens that the thing with the highest posterior probability is also simple in some sense. Yes.
So what if it just so happens that the simple complexity, which is the best fit scenario, is you have reasons to believe that it's too simple for reality. For example, if your different orbital parameters, the frequencies of these orbital parameters are multiple of each other or almost multiples, you could think that the model will identify the frequencies of your data as the simplest way of seeing it would be that you just see it's basically an aliasing problem, that you only see the lower frequencies, or because there are multiple of the highest frequencies. So you would get by this principle a simple fit with let's say obliquity, which will make you oblivious to the precession parameter variation. You see what I mean? Like by selecting a too simple model, which is statistically in the Bayesian sense correct, you may simplify reality too much if you have reasons to believe that the signals you see are multiples of lower order.
What you're describing is that you have a prior which is strong enough to override the likelihood.
Okay.
So if you put this strongly in your prior, that this has to be there, then you just don't leave the choice to the model to include it or not. You just say this is here.
Okay.
Okay, so we had the posterior probability, which basically was saying we have a parameter box. This is the box this is where my parameters live. They can't go outside that box. They are not allowed to go outside that box. And in that box, among the pool of my candidates, I have a region which is preferred. But you see that I just rewrote the exact Bayes formula that I wrote before, but I added the n, which in fact was implicit in the previous formula. It's like everything we said so far was assuming that the number of knots was fixed. So inside that box of parameters with the number of knots, that box with the number of knots fixed, I have preferred estimates of my parameters. But the evidence allows you to determine if you want a different box, if you want a bigger box, where you can put your model and your parameters and have some more freedom to fit your data. So back to my example with the polynomial. The likelihood was increasing with the degree of the polynomial. The evidence shows a peak at 3. So you were right. Well, actually, you were right because I know what I used to generate the data, but the log evidence, the evidence picks up that 3 is the correct answer. The BIC also finds the lowest, is also lowest at 3. The AIC does not distinguish too well between 3 and 4, but 4 is also okay. I don't think there is a general rule that the AIC is the BIC is always better than the AIC. It's just that it so happens that on this example, the BIC is correct. But also you can see that the log evidence is more peaked. It's like it's more discriminative.
Say again, what is the log Bayesian evidence? What's the definition?
The Bayesian evidence is, so it's this. So it's the integral of the data, knowing the model parameters times the probability of the model parameters.
Yeah, but there is no reference to the number of parameters here.
So
just
this is
implicitly.
So the evidence is a scala computed for each number of parameters. So each model with a different number of parameters is characterized by a log evidence. So basically for each number of parameters, you have a likelihood and a number of parameters, so you have a BIC, and you have an evidence, and you have an AIC. So as a function of the number of parameters, as the function of the degree of the polynomial in that case, you have a BIC, an AIC, and a log Bayesian evidence. This you want to maximize, these two you want to minimize.
And in this case, it seems that the parameter that discriminates the most is the simplest one, which is the Bayesian evidence.
So it's the simplest one in the sense that it's the most natural one that stems from the theory, but it's not the simplest in computational sense because this is an integral here over 10 parameters. And this is the whole problem. I mean, there are literally tens of thousands of articles, maybe hundreds of thousands, which deal with the numerical estimation of the evidence, because estimating an integral over high dimensional spaces is very hard. So in that case, you see that the contrast is higher with the evidence, and it's kind of expected because this is the real thing, and this is just an approximation. But the cost of computing this is much, 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 much higher than the cost of computing this. So this is why in AstroGeoFit, since we have potentially 50 knots in the model, 5 frequencies with phase, amplitude, frequency, and so on. So we have models with 50 parameters. We don't compute the evidence, but we compute these two. Okay, so these were my models, and this was the true model. Okay, so yes. So in the time depth function, what plays the role of the degree of the polynomial, the complexity of the model, is the number of knots. So I could have 4 knots or 8 knots. And just like all the polynomials of order 2 are contained in the polynomials of order 3. All the models with equispaced knots with 4 knots are included in the models with 8 knots. So the model with 8 knots is just more flexible than 4 knots. So it will fit the data better. It has to. Or you have a problem in your numerical method. That's actually a good way to diagnose if you have a problem with the maximization of the likelihood. Is if your model is more flexible, but you have the likelihood is not as good, it means that the algorithm has a problem. So in that case, so this is a simulated example where you have the sedimentation rate with 2 knots, 8 knots, 16 knots, and you see that as you increase the flexibility of the model, you're closer and closer to the true sedimentation rate that was included in the data. And at some point, you see that you have captured basically all the relevant variations. And as you increase the complexity of the model, what you increase is just the error bars. Because you increase the degeneracy of the model. So it's like you're already there, but you add more complexity. So it's like some of the parameters are going in different directions because it's not going to change your reproduced models. So you just give more and more freedom. Think of this, it's just like you have an equation with too many unknowns. So your equation is degenerate. It's like you want to solve a linear system. This linear system has more variables than it has constraints. So the variables can go anywhere. Here, this is the probabilistic version. It's like your problem is under constraint. And if you compute the AIC, the complexity of the model you select is 24 knots. And visually, it seems pretty convincing. It's like, here, I don't have so here, I don't have at all the first oscillation. Here, I see the low frequency component. I still don't see the high frequency components here. Now I see it. Now I captured all the correct variations in all the scales of variation in the model, in the data, sorry. And from that point on, I just increased the degeneracy of the model, and adding more flexibility does not give me an improvement in likelihood. So here is the AIC as a function of the number of knots. And this is something that so since we don't have an integral, but we have only the maximum likelihood, this is something that you can do at the genetic algorithm stage before doing the MCMC. Another example, so this is real data, and in that case, so this is the nominal time depth relationship that's been, well, sedimentation rate, which has been done by eye. So this is not the ground truth. We don't know if this is the real thing, and when there is an agreement between the two, it might, well, even when there is no agreement between the two, it's like we don't know which one is best, if it's the tuning done by eye or if it's the tuning done by AstroGeoFit. Right? But anyway, if you're in the AstroGeoFit framework, the model complexity that's going to be selected is this one. So the model thinks that you still need quite a bit of granularity in your time depth model. Not that much, but more than this. Another example with real data, where the bias variance trade-off I was talking about earlier is particularly apparent. Here I have a very stiff model, very small error bars. Here I have a very flexible model with very high error bars. And the correct model is in between, where I do have some variation, but it's not as it is a compromise between the complexity of the model and the agreement with the data.
And maybe it can be said that it doesn't mean that the sedimentation rate doesn't change more than what is shown in the fit. It just means that your data doesn't allow you to show it.
Yes.
Am I right?
Yes, exactly.
So if we know that we have like jumps in the sedimentation rate, before testing the AstroGeoFit, it can be useful to pre-tune the data set, actually, so that we avoid these jumps in sedimentation rates.
Yes, I don't know what would be the best way to do this, but
I'm not sure it will add anything if you do this. I'm not sure it will not be exactly the same thing. The only thing that will matter would be to decide some, but we have not input this possibility yet, but to decide the grid of the point. If you know there is a place where there is a high variation, you could increase the mesh. And that's totally compatible with everything that is done in AstroGeoFit. The only thing is that we have not implemented this feature. We could do it. Right now, it's just uniform grid.
yes.
So you can increase the grid, but increasing the grid increase globally the number of parameters.
Yes.
So if you know that in some place you have a big jump, you increase locally, so you don't increase that much the number of parameters, which would be better.
Yes. So maybe, so suppose that not only the amplitude of the knots, but also its position here can be modeled. If your sedimentation rate is like this, then it's better to have 1 point here, 1 point here, 1 here, and 1 here. Yeah. Yes, but the price you pay is that per knot, you have an additional parameter, which is its abscissa. So this is something we need to test, but you see that the space of possibilities grows very, very, very rapidly. It's like the way you tune exactly the model is, there are many ways to do it. Okay. And earlier, we said that there are two questions we can ask in model selection. Who's the best candidate? But also, should I fill the position? Should I hire the best candidate? And in the case of geological data, is there some astronomical signal in there, or is it just something else? So the statistical framework to do this is not model comparison as we've seen, but it's what we call the null hypothesis test. So this is closer to what Popper had in mind, Karl Popper. It's like, I can never validate a scientific hypothesis. I can just say that it is rejected or it is not rejected. So my hypothesis is the data is just noise. I can reject the hypothesis that the data is just noise, but it doesn't mean that I accept that this is an astronomical signal. It's just, this is not noise. Or I don't reject the hypothesis. So we've seen that the data can be, so the way we test it statistically is saying the data that I have was generated from a certain statistical distribution, which is called H0. And so, for example, I assume that my data was one realization of this process. So it could, it is the, and this process generates stuff that looks like this. So the test in AstroGeoFit is, okay, this is my null hypothesis. I'm going to generate stuff from my null hypothesis. So for each mock data set that I generated with this null hypothesis, I'm going to see if when I fit the full AstroGeoFit model, so the exact one I used on my data, if I fit it, do I retrieve an astronomical signal which improves my fit of the data? So the thing is, if my initial data were pure noise, if I fit AstroGeoFit, I look and I see how well the astronomical signal fits with the data, it shouldn't be better than if I do the same with mock data, which is generated from my null hypothesis, because in that case, my data would be just another instance of the null hypothesis. So here, I'm sorry, I tried to make it, to remove as much of the statistical formalism as possible, but this is, this is inherently something that you do with statistical formalism. So if you want to discuss it in more detail, feel free to come to me afterwards. So I'm going to have, so each time I generate mock data, I'm going to have a metric saying how close the retrieved astronomical signal is to the data. So I have a histogram of these R-squared values of these agreements, and I'm going to see if the R-squared value I have on my real data is a typical instance of this or not. Okay, so suppose this is the data. So in that case, this is a simulated example, but for the sake of the presentation, we are going to assume that this is the geological data we have. And this is the astronomical signal we fitted. We also have fitted a noise model with a covariance C. Now, with this model, this fitted model, I'm going to have to compute a metric which gives me the agreement between the data and the signal, weighted by the noise. So the closer my astronomical signal is to the data, the closer this is to 0, and the closer this is to 1. So 1 means that I have a perfect agreement between my astronomical signal and the data. So yes, this one, we are going to call this R the reference one. This is the data with the data at hand. Now, with this data, I'm going to do another thing, which is to adjust to fit an autoregressive model of order 2. And so without the astronomical signal, I'm saying this is just noise, and I'm fitting, and my hypothesis is that it was just noise, so I fit just a noise model. And the null hypothesis is that the data was generated from this noise model that I just fitted. Now, with this noise model, big noise model that I fitted onto the data, if my null hypothesis is correct, the data is no different from other realization of this noise model. So I'm just going to generate a bunch of mock data sets, and every time I'm going to fit the whole arsenal, the whole AstroGeoFit model, and try to see what the astronomical signal would look like. So in that case, this is what the astronomical, so this is noise, but you see that we fit something that looks a little bit like an astronomical signal. Here also. This is a bit worrying to me. Yes, it's like you use AstroGeoFit. This is the fit that you retrieve. You're like, yeah, of course I have an astronomical signal. Well,
many papers look like that.
No. Not any good ones.
So, okay. So
from 0 to 0.7, okay, but at the end it's growing.
Okay. Okay, I'm not. My eye is not as trained as yours. So, but to me, it doesn't look so bad. But the point is that in fact, this is kind of simple. It's like, okay, well, if the data was pure noise, would I still have an astronomical signal that looks good, or is my astronomical signal looking better than that? So each time so I recompute a measure of the fit of my astronomical signal, my fake astronomical signal on my fake data. So this is the simulated data, this is the fake astronomical signal. Each time I do a different realization of my fake data, I have a new version of the agreement, a new value of the agreement between the model and the data. So I can plot the histogram of these values. So this histogram means this is the ballpark, if my data were pure noise, where the agreement between the data and the astronomical signal would be. And so one way to think about this is the mean value, this is the typical value, and I look at the difference between the value on a particular mock data set and the mean value and see, well, so the standard deviation of this, and I will say that if my data was a realization of the null hypothesis, if it was no different, if it was not different from the mock data set, I would have a value of R which is close to this plus minus the standard deviation of this. But in that case, the R value that I have is very high. So my data is not a typical instance of the null hypothesis. It's the agreement between the data and the astronomical signal in my real data is much higher than if the data were pure noise. So in that case, so in AstroGeoFit we do something which is slightly more complicated, but I think that's enough statistics for today. So we compute basically the number of times that we had an R higher than the one we saw on the data. So how many times did we have an agreement between the fake data and the fake model that is better than what we see on the data, divided by the number of simulations? This is what we call the false alarm probability.
Nathan? So what you showed was with a random noise, right?
So with an autoregressive noise. And you see that when I generate fake data, I still have correlation, right?
So is this because the correlation is somewhat of a periodic signal, or like, do you see what I mean? My question is, if the noise is somewhat periodic, does this substantially affect the retrieval test?
Yes. So in that case, the noise is not periodic.
Okay.
But it's correlated.
Yes.
It has a certain memory.
But you could imagine processes that like noise your data, which are themselves periodic but not astronomical.
Exactly. So this is actually an important. This is something I wanted to insist on in the conclusion, but I'm going to do it right now and do it twice and do it another time in the conclusion. So it's like, here we are testing that the data is an AR2 process or not. But if the data is noise, but it's another type of process, you could have something like this, but it's just that you reject the hypothesis that the data is this particular type of noise.
If you had a periodic perturbation that is not astronomical, it will be, through AstroGeoFit, it will be identified as a periodic component.
Yes.
Okay. So you extract, but not, except that you will not identify it as a periodic component depending on the prior you put to the frequency that are in the signal. If you have some periodic perturbation that is not in the range of the frequency you are looking for, it will be interpreted as noise. It will not be interpreted it will not give rise to an astronomical signal.
And this is actually also an important point in statistical analysis. It's like you could have a periodic signal which is fitted by a periodic component in AstroGeoFit. Because the model speaks mathematics and the model speaks periodic signals. But you speak geological signals. So the thing is, if the model finds a periodic signal, it's your responsibility to interpret it as an astronomical signal or not. It's like you have all these tools to force the model in certain frequency ranges because you think that the astronomical frequency is in this range. But making the translation from the mathematical model to what it actually means for the geological record, it's still the responsibility of the analyst.
There is in a search for extrasolar planets, and Nathan is really a specialist of that, there is a typical periodic signal which disturbs the observation, which is the rotation of the star if you have a dot, a spot on it, or some activity. So it will give you a periodic signal that you can interpret as a planet if you are not careful, but that is in fact the pure rotation of the star. Maybe you can comment on that.
Yes.
Yes, he commented. He said
yes. Yes.
As we are on the topic, a related question. So I think other methods like time-opt maybe do the same, but with an autoregressive thing of first order. I would have to check. But so, like you rightfully say, it always depends on the assumption of the type of noise that we model. So I was just wondering, could you, or maybe it's a naive question, have a null hypothesis distribution where you combine different types of noise, that you test for different types of noises in a way to make it slightly more robust?
Yes. So one way so you can do if you wanted to do this, what would you do? You could do, I see two things you could do. First, you can perform the test assuming different types of noise. So you have different tests. So you can test, is this compatible with an AR2 or an ARMA model with a moving average component or whatever. Or you could generate a type of noise, which is, for instance, with the probability 1/2, I generate an AR1 model, and with the probability 1/2, I generate an AR2 model. So you have a sort of composite noise model. I think the first option is more robust because you still understand, you still have interpretability of the result. You want to keep things simple enough so that the result has some sort of identifiable meaning. Okay. So, I mean, here this test is not perfect. So if I had a theoretical perspective trying to prove that the test was doing exactly what it's supposed to be doing, well, this is just an approximation of what we should be doing. But still, I think it's reasonable. Yes.
Yeah, it's just to make sure that I've understood your graphs.
Yes.
On the next slide.
Yes.
It's the value of the R2, right? The
Yes.
X. Yeah, because you put depth, so I mean, I'm a bit confused.
Sorry. I copy-pasted the plots. Yes. No. This is R squared. Yes. 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 Yeah. Well, otherwise, it doesn't make any sense. Sorry. Okay. So this is an example of this test performed on the data. So you see that the red value that I showed before, it's not here. It's the average value on the different realization of the genetic algorithm on the real data. And this is, this on the other hand has the same interpretation as what I showed before. So if my null hypothesis is true, if the data were pure noise, the agreement between the data and the model would be in there, but it's there. And here, the difference is particularly clear. And in AstroGeoFit, you can do this for every number of nodes. Because to do this, you need to select a number of nodes to run the genetic algorithm. So at each number of nodes, you can test the hypothesis that the data are pure noise. Yes.
So can we also use that in addition to the AIC and BIC as a way to see, for example, when I can see so the difference is increasing when we increase the number of nodes here in the values of the R2, but at some point it's not increasing that much. Like, for example, there's not so much of a difference as I can see in the R2 value between the 16 nodes and 24 nodes for ADP 1262.
Yes, but I mean, here it's kind of contrary to the spirit of the test to try to compare different nodes. It's more about, like, suppose for this number of nodes for this model that the data were pure noise, would I be correct in assuming that it's just noise or not?
There is another thing. The AIC is very quick. This is much more time consuming. So you don't want to do that. You do that at the end when you write the paper to convince people. Yes. Because otherwise the referee would say, what about false alarm probability? Because basically, if you really see by your habit, that's the signal in the data, then you will end up with a good false alarm probability. But we were surprised to see how much. So I am not sure you can totally. Can you comment on that? Because these numbers are quite phenomenal. When you have a false alarm probability of 10 minus 18.
Yes.
Okay.
No, but I mean,
it means that there is some signal in the data.
Yes. So it means that.
It doesn't mean that your model is correct.
Actually, I think one way to think about this is with the bias variance trade-off. It's like our model of the noise is very specific. It's an AR2 model. So you can be extremely different from an autoregressive model of order 2. I'm not too surprised that real data has a false alarm probability of 10 to the minus 18 of being different from an autoregressive model of order 2. But now, if you think more broadly about the hypothesis, the data is noise, it's not astronomical signal. So maybe it's AR2, maybe it's ARMA, maybe it's another type of noise, maybe there's no non-Gaussian noise, maybe. So it's going to blur everything. So maybe at some point, one of the noise models that you're going to try is not as far as the data as the AR2 model. Because your null hypothesis is too stiff, it's too rigid. So, I mean, suppose you do frequency analysis, you compute the Fourier transform of some data. And your null hypothesis is that the data is noise, but white noise without correlation. If the data is red noise, and I'm sure this is a situation that's familiar to, if you compute the periodogram, the Fourier transform of a geological time series, you always have low frequency power at low frequency. So if your null hypothesis is that the data is just white noise, it's going to be rejected with a very, very high confidence. It's like, no, it's not white noise. But it's still noise. And here it's similar. It's like you can reject the hypothesis that the model is not AR2 noise, but you can't reject the hypothesis that it's any type of noise. So the fact that it's 10 minus 18 is reassuring. So if it was 10 to the minus 3, for example, I would be much less confident in the fact that this is not noise. But Now 10 to the minus 18, it's like, okay, it's really not at least this type of correlated noise. Yeah. And I think this is a reasonable compromise between something which is really informative and not absurdly time-consuming. Okay, so to conclude.
And just the analysis is made on the fit algorithm,
yes.
not on the full MCMC component, so that it can be much faster than if it were on the MCMC.
So yes, we've seen, so basically we had two questions. Who's the best candidate? Should I hire a candidate? The BIC and AIC, they have a strong theoretical backing as approximations of the selection of the most likely complexity. So here, what we are doing is actually selecting the complexity, the number of, here the degree of the polynomial, but in AstroGeoFit, the number of knots which is most likely. And the second question is, should we believe that there is an astronomical signal? And in that case, you have also a test in AstroGeoFit, but keep in mind, as we've said abundantly at this point, that the null hypothesis here is that the data were generated with an autoregressive model of order 2. And even if it's rejected, the data could be another type of noise. So you can think of this as, you want to make parts, mechanical parts. You can do it by hand, or you can do it with a big machine where you need to specify stuff. If you want to build a plane, you will not build your parts by hand. So AstroGeoFit is kind of similar to the big machinery, which allows you to do very complicated things, but you still need to specify what you want to do, right? It's like it's not just one big machine where you put everything, and whatever the result, you take it as the word of God, and this goes straight into the paper. Even if there is a big machinery which does everything at the same time, you need to keep in mind that the results, the statistical results of the algorithm need interpretation. Thank you for your attention.
Is there any question?
So are there any formats of noise that are implemented automatically in the AstroGeoFit besides this one at the moment?
At the moment, I don't think so. I don't know. Arsene? Yeah. Can you do the null hypothesis with another type of noise? No, not yet. But yeah, it would be good. Yes.
Okay, we'll stop now. We'll make a break.